So my lectures are going to be on Khovanov homology or Khovanov homologies. And I'd like to begin with an imaginary conversation. And this imaginary conversation is taking place in, say, 1959 or thereabouts, with the great algebraic topologist Norman Steenrod. So you go up to Steenrod and you say, well, Professor Steenrod, I'm interested in inventing something called link homology theory. What do you think that should be? Can you give me some ideas of what this should be? So then Steenrod thinks for a little bit and then says, well, so we're talking about what the expectations are of link homology theory. Can you read this up the back? Is that okay? Okay. So what are the expectations of link homology theory, perhaps if we're having this imaginary conversation? Well, the first thing Steenrod would probably say is, well, link homology theory, we know about homology theories, what you should have is you should have some kind of a functor. And there should be a functor from a category of links, let's call it H, to some other category. And this other category, well, we might not specify what it is, but secretly we're thinking that this is something like vector spaces or modules, something like that. And you would explain that your notion of equivalence for links is isotopy. So Steenrod would insist that whatever this category of links is, that you have isotopies as morphisms. So this should be some category of links where at least isotopies are morphisms. And then, in this imaginary conversation, Steenrod would start to tell you some properties that this functor ought to have. The first one would be that it's invariant with respect to your notion of equivalence. So such that if you have an isotopy then when you apply your functor, what did I call it, H, this should be an isomorphism. The second thing that he'd probably mention is that you should have some kind of normalization procedure. Steenrod would be thinking of the fact that for his axioms for homology, that the dimension axiom, the homology of a point is very important. So you have some kind of, so this I guess this is invariance. You want some kind of normalization. So you'd want to specify the value of, say, the unknot. And then, well, you don't want to work out everything. If you have two links which are disjoint, then there should be some way of combining those. So if you have L0 disjoint union with L1, then, well, I'm not going to specify how, but there's some way, let me just write box, of combining the value of L0 with the value of L1 to give you what happens when you have a disjoint union. And finally, what might Steenrod say? Well, this is all very well, but you need to be able to calculate something. So he'd also probably insist on having some kind of calculational tool. And what to say about this? Well, what sort of calculational tools would he be aware of? What would he be doing? Well, in cohomology or in homology, of course you have things like excision, you have Meyer-Vittora's long exact sequence. So the kind of thing you're thinking of is something like that. So something like a long exact sequence. Where we're thinking of maybe Meyer-Vittora's in cohomology. So after that, you would say, well, how am I going to do this? And one of the things that he might reply to you would be, well, you're not going to pull it out of thin air. You're probably going to make contact with something that you already know. So, for example, cohomology, if you take the cohomology groups of a nice space, and then you look at the alternating sum of the dimensions, then you get back the Euler characteristic, which is an invariant which is much older, something you know already. So if you're going to invent a link homology theory, you should expect to find something that you know at some point. So then you're feeling emboldened, and you say, okay, well, maybe I can find a complete invariant. What do you think about that? There he'd express some doubt, and he'd say, well, that might be a little bit hard, but if you think about algebraic topology again for a moment, think about homotopy groups. Homotopy groups, not a complete invariant, but if you restrict to CW complexes, then if you have the homotopy groups the same as a point, then that actually tells you that your space has the homotopy type of a point. So perhaps you can hope for something of the form homology of your link, perhaps a knot, is the same as the homology of the unknot. Then you might hope that your knot is equivalent to the unknot, because that's the sort of thing that we can get out of topology. And then he'd carry on and say, now he's enthusiastic, he'd carry on and say, well, also you might try and generalize this. Well, how do I do that? Well, you need some ingredients. What ingredients do you have? You don't know, but you have a suspicion that it's got something to do with the Lie algebra SL2. Okay, says Steenrod. Well, there are lots of other Lie algebras, so you might have a whole family. You might be able to generalize what you've got. So then you leave, and as you're going down the corridor, he shouts after you, don't forget spectral sequences. Now, my series of lectures, the aim of my series of lectures is more or less to fill in some details of that vision that I've just given to you. Let me give you some references. So they're in the handout that you have. There are a number of introductions to Khovanov homology or Khovanov homologies, and my aim is not to give a sort of standard introduction, because this has been written down, and it's been written down well and many times. And so here are some of the references. What I want to give you over the lectures is a kind of guide. I will talk about some details, but I don't want to do what the standard course on Khovanov homology would now do, which is spend about 3 hours talking about the definition. I don't want to do that. So let me give you some references nonetheless. Well, they're written down, so I'll just write the numbers down for posterity. So all the references I give on the board will be, and in here, in fact, will be just the archive numbers. I find that easier. So this is a paper by Dror Bar Natan, where he explains very well a construction of Khovanov homology. There's another more recent paper by Alex Shumakovich, which is this one, which is also a very nice paper where you can find the elementary facts of the theory. Khovanov's original paper is this one. And there's also a set of notes that I wrote, which you can also look at. In fact, this set of notes, it's called 5 Lectures on Khovanov Homology, and it was the last time I was in Marseille, in fact. So 8 years ago, there was a meeting, and I was also giving 5 lectures, or 5 hours of lectures on Khovanov homology. So it seems like it's a kind of payment I have to make, coming to Marseille, a rite of passage to give lectures on Khovanov homology. Okay. So let's begin with an existence theorem for Khovanov homology. So there exists a covariant functor kh from links to finite dimensional F2 vector spaces. So what's links? I said that we should specify some category of links. So here, links is the category with objects, oriented links in S3, and morphisms being compact, oriented surfaces in S3 cross an interval. So the boundary of such a surface should live in the two ends of the cylinder. And it's a morphism between a link L0 and a link L1 if the boundary is precisely those two links that you find at the end. This is a standard notion of link cobordism. Okay, so there exists a covariant functor like this, such that firstly, if sigma is an isotopy, then kh sigma, which goes, sorry, maybe sigma should be an isotopy from L0 to L1, then kh sigma, which is a map of vector spaces, is an isomorphism. The value of the unknot is just 2 copies of F2. If I have a disjoint union, then I simply get the tensor product of the two constituents. So this would be a little surprise for Steenrod, this tensor product. He would probably be expecting a direct sum, because that's what happens in homology. But here we have the tensor product. And the last point is that there's an exact triangle. So, sorry. Yeah. So if L is represented by a diagram, and a small piece of that diagram looks like this, so there's nothing else in that in that small piece, then there is an exact triangle of this form. So what I've done here is I've taken my small piece and I've replaced it by a slightly different small piece. Now this isn't quite enough for the existence theorem that I want. It's almost enough, and we've given the pieces demanded of us from our conversation. But actually, if you're very quick, you can possibly see that there are a number of solutions to this, some of which are a bit trivial. So I want to specify something more, because you see this functor isn't just a single functor, it's a family of functors. And you have one of these for each pair of integers. So perhaps this should be part 5, actually. So in fact, KH carries a bigrading. And I want to tell you how some of these constituents behave with respect to this bigrading. So first of all, so with respect to this, if sigma is a link cobordism, then the induced map on vector spaces KH sigma has got bigrading 0 in the first coordinate and the Euler characteristic of the surface sigma in the second coordinate. The generators of the unknot also have some bigrading. And they live in 0, 1 and 0, minus 1. And most importantly of all, this exact triangle, well, it unravels to a long exact sequence, but in particular I need to tell you how the bigradings work for that. They are written down in these notes, but again I want to just write this up, but I should make sure I get it right. Okay, so there are two cases. So the exact triangle unravels. And the first case is if I have a negative crossing, which looks like this. Remember, we have oriented links, so crossings come in two different sorts. So for each j, there is a long exact sequence. So this is I, j plus 1, and here I do the replacement like that. And here I have the the co-boundary map, which increases this by 1, so I end up in k I plus 1 j of this again. So that's the first case. And then there's a case for positive crossings. There's something, well, there are two things here which you should be questioning. One is that I've used here an undefined symbol, okay? And the other one is that I said that the functor kh took as input oriented links, and here I've written down something which is not, which does not have an induced orientation in a consistent way. So what I do is I choose an orientation for this. And that choice determines this W for me. So here W is the number of negative excuse me. It's the number of negative crossings in the chosen orientation for this guy minus the number of negative crossings in this one, the original diagram. So that's the first case. And the second case is when I take a positive crossing. I think you all have the notes, so maybe I should write it down for the purposes of the internet. This is being recorded, so maybe I should write down what the second case is. So just bear with me. The second case is the positive crossing, where I have the following. It's I minus 1 minus C, this one here. And then this carries on. So that's the basic that's the basic piece. Where C, again, I have to choose an orientation for this, and C is the difference in the number of negative crossings. There. So that's what we have. So this is our starting point. It's an existence theorem. There is such a functor, and it satisfies these properties. How you construct such a functor is something you should be interested in, because of course constructing such a functor is the proof of this theorem. But I'm not going to do that right now. What I want to do is I want to see what we can get from just from this theorem. Okay, And we will talk a little bit about the construction, but mostly I will leave you as a homework exercise to read about the construction. I will say something about it, though. So the first thing we might try and do is reduce the amount of work we have to do. And one way of reducing work is to prove that you only have to do half what you thought you had to do. And in this case, what this means is that depending on the number of components of the link that you're dealing with, half these groups are 0. Either the, well, I'll write it down. So here's a proposition. Let me just check my notation. Yeah, okay. Well. So if L has an odd, respectively even number of components, then all the even groups like this, so KH star even, respectively the odd ones, are trivial. So that's good because you only have to do half what you first thought. Now, why is this true? Well, if you do know the construction of Khovanov homology, the one given by Khovanov, which I know a number of you do, then you know this by construction. But that's not the point here. The point here is that it follows from this existence theorem. And the proof is rather simple. So the proof of this is simply an induction on the number of crossings. Using the following lemma. So the lemma says that in the long exact sequences above, first case, if the strands appearing are from the same component, then omega is odd. What did I call it? W. Omegas and W's tend to get confused for me. But so W is odd and C is even. And the second case, if the strands appearing are from different components, then W is even and C is odd. Can you still read the bottom of the board? Yes, good. So this lemma involves absolutely nothing at all. It's a tiny combinatorial exercise which you might want to do if you don't want to concentrate. But from that, you see, then you use your long exact sequence, and it falls out almost immediately that you have this result here. Okay, so after this, so now use the long exact sequence. I'm sorry? Yes. Thank you very much. Yes, this should be j plus 1. Yeah. Well, the second way we can try and cut down our work is to reduce the number of links that we have to calculate. So the proposition in this case is that if I take the mirror image of a link, then I can compute that in this way. And the proof of this goes something like this. You see there is the identity cobordism, which looks like this. So here I have S3 and here I have S3. There's another cobordism which I have. So I'm thinking of my cobordisms going down the page. There's another one which I can write like this. So I take the identity cobordism and I bend it over, and if I bend it over, then that means that I get the mirror image here, just by some elementary geometry. I also have one that looks like this, again by bending things over. And what this gives, if I look at this one here, I have a functor. So this gives me a map from KH of the mirror image disjoint union with L to KH of, well, to where? Well, this is the empty link. Perhaps I should have specified that what that was as well. I'll just take that to be F2. Maybe that should have appeared in my in the theorem. I think in the notes maybe it did. But this is simply the tensor product. So I have this map. This is a bilinear form. And you see, if I compose these two morphisms here, this is the kind of thing that you do in 1+1 dimensional TQFTs all the time. If you're familiar with that, then this will be a familiar kind of argument. What you're being told, if you compose these two cobordisms, you'll see that this one, the composition, looks at the end of the day like this, which can be straightened out into the identity. And the identity, well, that induces the identity map on the induced vector spaces. And because our category of links, and I didn't say it, but I should have, morphisms, so these link cobordisms are considered up to isotopy, it means that the map induced should be the same thing. And if you're familiar with the kind of arguments in 1+1 dimensional TQFTs, this is telling you that this bilinear form is non-degenerate, and because we're in a graded setting, if you get everything right, then you'll see that what that means is that you have this result here. So the one connection with other things that you've probably heard of by reading the promotional literature for Khovanov homology is it's supposed to have something to do with the Jones polynomial. And once again, if you know the construction of given by Khovanov of Khovanov homology, then it's more or less written into the definition that you get the Jones polynomial out. But once again, here we don't have that. Here we've just got our existence theorem. So let's see it come out of the existence theorem. So how do we see the Jones polynomial? Well, one thing we do know is that if we have a long exact sequence of vector spaces, then if we take the alternating sum of the dimensions of those groups, then we always get 0. So that's just a fact. Simply an exercise in linear algebra. So what we have, if we look at the long exact sequence that I wrote down, say for the negative crossing, then what do we have? We have for each j, the following thing is 0. Maybe it's still there. So there is the appropriate long exact sequence. So what do we have? We have the summation over I of minus 1 to the I, the dimension of kh I j plus 1 this minus a similar sum for the next terms plus where is it? That this is always 0. So that's just that statement about the alternating sum of the terms. Now I can write this down in a slightly different way. So if I let, say, P of D be the alternating sum like this. Sorry, it's the sum over I. Yes, it's this, and then Q to the J. So I'm introducing some variable Q. And then I take the dimension of kh ij. So if I define PD like this, then this statement here, including the for all for each j bit, becomes the following thing. It's the same as saying that q to the minus 1, p of this, minus p of this, plus minus 1 to the power w q to the 1 plus 3 w p of this is equal to 0. So you have to do a little bit of a calculation. So if you take this equation here and you take the coefficient of q to the j, then that tells me, it gives me precisely this. But of course I can play a similar game with the other long exact sequence. So similarly, from the long exact sequence from the positive crossing, I get that minus 1 to the power w, 5 plus 3w p of this one minus p of the positive crossing plus q p of this one is equal to 0. And now you see with these two equations, I can try and get rid of this one here. And if I do that, I get the following. Q to the minus 2 of the positive crossing minus q squared of the negative crossing plus q inverse of p of this oriented one is equal to 0. And then if you put q as, just to make this very explicit, if you put q equals minus t to the half, then you recognize this, right? You recognize this as being the Skene relation which characterizes the Jones polynomial. So if you have an invariant taking values in Laurent polynomials, satisfying this relation, then up to perhaps the value of the unknot, you have the Jones polynomial. Okay. So by the uniqueness result, which I guess I just gave to you, for the Jones polynomial, you know that this quantity here, that p, is actually giving you the Jones polynomial. So this gives the Jones Skene relation. And since p of the unknot, perhaps when I make this variable change, it's equal to minus t to the half plus t to the minus a half. What's the grand conclusion of all of this? Well, we've actually proved the following proposition, that if you take minus the so if you take the value of the unknot, so minus t to the half plus t to the minus a half, times the Jones polynomial, then that is equal to this polynomial p with that variable change. Okay, so the polynomial p depended, I guess the definition is still on the board. It was a sum of dimensions of the Khovanov homology groups. We worked through using the long exact sequences, and then we conclude using the uniqueness theorem of the Jones polynomial that what we're seeing is actually the Jones polynomial. Now again, this is something that if you know Khovanov's construction of this functor, it's designed to do this, but you don't need that construction. It comes from the existence theorem. Now the next thing that I want to point out is that if I focus on the unknot, then this functor, the value of the unknot, it actually gives me something slightly more. There's a little bit of structure there, and it's this. So the further structure well, the Khovanov homology of the unknot, well, I told you exactly what it was as a vector space, but in fact it's a ring. Actually, it's even more. It's a Frobenius algebra. But for us, let's just say it's a ring. Why is it a ring? Well, because I have the unknot, and I have another copy of the unknot, and I can consider this link cobordism like this. So again, if you're familiar with 1 plus 1 dimensional TQFTs, this is kind of standard. This induces a map from the Khovanov homology of the unknot, let's just call it U, tensor, same thing, to the Khovanov homology of the unknot. And so this gives me a multiplication. I also have a unit. And why do I have a unit? Because I have that link cobordism like that, which gives me a map from the ground field to the Khovanov homology of the unknot. And various properties of the topology of surfaces tells me that, gives me associativity of this operation and so on. So let's give this a name. Let's call this U star star. So it's a ring. Now this ring acts on the Khovanov homology of any other link. So if I have a link L, then its Khovanov homology is a module over U star star. And why is that? Well, it's the similar picture to this. If I have the unknot here, and I have my link here, with a little bit poking out like this, then I can consider the cobordism, which looks like something like this. Okay, so this is how so this gives me a map from U star, well, it's from the KH of U disjoint union L, which as we know is this. So this gives me the action of U star star on the Khovanov homology. Now, a priori, this could depend on a number of things. In particular, I've chosen this cobordism to join up at some particular point, but more importantly, this particular point is on a component of my link. And even though this doesn't follow from the existence theorem, this action is independent of those choices. So if you're an expert and you're being nervous, I remind you I'm working over F2. This is not something that immediately follows from the existence theorem. And in fact, even more is true. In fact, there exists a slightly different thing I can associate to the link L, such that the Khovanov homology of the link is the tensor product of this new thing, which I haven't told you about yet, tensor U star star. So this is giving you the structure of the Khovanov homology as a module over U star star. And again, this does not follow from the immediately from the existence theorem. So what this new thing is that it's a reduced version of Khovanov homology. So again, let me just state this as the theorem. So this is the existence of reduced Khovanov homology. There exists a functor kh tilde from links to finite dimensional F2 vector spaces satisfying if I have an isotopy, then I get an isomorphism. The value of the unknot is even simpler than it was before. It's just F2, and this is also bigraded, and this is in degree 0, 0. What else do I need? The disjoint unions. Can still be expressed like this. And I have long exact sequences exactly as before. And I really mean exactly as before. The indexing is the same. Okay, good. I have until past, don't I? Yeah, okay. Perfect. So one thing we haven't done yet is seen any examples whatsoever. So perhaps we should. Now, previously, with the result about the mirror images, which is over there on the left-hand board, it might be telling us that we can't say anything about mirror images because it might be that the Khovanov homology of any link is actually symmetric with respect to this negating the indices. That might be the case. I mean, in fact, it's not the case. And this result tells us that if it's not the case that everything is symmetric with respect to that involution, then we can detect the difference between left and right, between a link and its mirror image. But in order to know whether this kind of thing is true or not, let's at least do a small calculation. So if you know this kind of thing before, this really is now for the beginner end of the spectrum rather than the expert end of the spectrum. I just want to spend 2 minutes doing a calculation. So how do you do calculations? Well, you have a calculational tool, which is your long exact sequence. So you use it. So let's calculate in 55 seconds the Khovanov homology of the Hopf link. So here is my picture of the Hopf link. like this. I'm going to focus on this crossing here. So my piece of diagram is that piece there. I have two other things associated to this. So this is the link L. I'm looking at the crossing which looks like this. The two other pieces of the long exact sequence, have they gone now? They possibly have. Look like this. So that's the one, the one that looks like that. But this, as you can see, is actually the unknot. And the other one looks like this, which you can also see is the unknot. And if I choose the orientation which looks like this, then that's a negative crossing, I think. So I get C is equal to 1. And then I use the, does this go up? No. And then I have the long exact sequence, which has a piece or pieces that look like this. I'm going to use the reduced theory. I minus 1, j minus 1 of the unknot. So I'm going to plug these in already to kh of I minus 2, j minus 5 of the unknot again. Here I put the Hopf-Link. Here I have I j minus 1 of the unknot. And there's one more. Do I need that? Yes. I minus 1 j minus 5 of the unknot. Okay, so there's part of my long exact sequence. There's not very much homology in the unknot at all. One group is non-trivial. This one group could appear either on the left or the right of this group here. So the values of I and j which are interesting to me are the following. I is equal to 0, j is equal to 1, and I is equal to 2, and j is equal to 5, because they're the values that will give me the non-trivial group here. When I've in this first case here, what do I get? Well, the long exact sequence looks like this. It looks like 0 there, goes to 0 here, goes to k tilde 0, 1, L here, F2 here, and 0 here. So I conclude that that group is F2. And then the other one, I end up with it on the other side. So I conclude that that group is non-trivial. Okay, so the result of that calculation is, well, I can write it down as a table, and typically Khovanov homology is written down like this. Where I stick I along here and j here. And if I've got 0, 1, 2, 3, and so on, I've got a link with two components. So that means that I know that all the odd groups are hang on, what? What am I doing? I have an help. I'm supposed to be doing this computation in 55 seconds, and I'm running out of time. Never do computations on a board in front of an audience. Never, ever, ever do that. So my indexing has, no, that's not right. Yeah, I'm sorry. No, I have done this correctly. Do computations in front of an audience, but just know what you're doing. I'm calculating the reduced Khovanov homology. Now, the reduced Khovanov homology has this odd-even parity half the groups are 0, the thing we had before, but it's the other way round to this one. So if I have an even number of components, then all the even groups are 0. So fortunately, the world is at peace with this, and what we have is, indeed, we have a non-zero group in 0, 1 here, and so I've ignored the even ones, and a non-zero group in, maybe I've still done this wrong. No, I think this is right, in 2, 5, here. Phew. Okay, so maybe that took longer than 55 seconds, but not much longer. So as an exercise, particularly if you're a beginner, you should really try and calculate the reduced Khovanov homology of the trefoil and the figure 8 knot. Okay? If you haven't seen Khovanov homology before, you should do that, and the way you do it is like this. You use the long exact sequences. If you're an expert, I also have a question for you, which I've written down here, which is which knot in the knot tables, which is the first knot, which you cannot compute by using just the long exact sequences and previous computations in the tables. Now, for calculations, it turns out that the reduced Khovanov homology of alternating links is rather simple. And here's a proposition due to Lee. You'll find the reference, well, here's the reference actually, 0201105, reproved a number of times. And it's this, that the reduced ijth group of an alternating link is trivial unless j minus 2I is the signature of L. So in particular, if I draw these kind of tables that I've been drawing before, it means that it lies on, all the non-trivial groups lie on this line, which actually we can see here. There aren't very many of them, but there they are. And a consequence of this is that the signature and the Jones polynomial determine this completely. And the reason for that is that when you take that alternating sum that I did before, the sum, if you like, is across this. I mean, it's minus 1 to the power I, so things might cancel across here. But if we're lying on one line, there's nothing to cancel. So that means that the Jones polynomial and the signature determine this completely. Now, so far I've been working over F2, and the reason for that is that a lot of things are simpler if I do that. But there is also an integral theory. So, just roughly speaking, you can do the same working over Z. But there are some things to be aware of. There are some pitfalls, some things that don't work nearly as well. The first of these is that functoriality is trickier. So I'll say a little more about functoriality later, or in some subsequent lecture. But it's okay up to plus or minus 1. But getting rid of that plus or minus 1 is really quite difficult. What else changes? There's a reduced version. But remember before when I introduced the reduced theory, I said it doesn't depend on those choices. Well, not so for the integral version. So this depends on the choice of component. And the relationship to the unreduced theory, which was written down right here, which was a very simple relationship in the when we were working over F2, is slightly more complicated, but the relationship is given by an exact sequence. So the relationship to unreduced more complicated. And here's the exact sequence if I've got room on this board. So the reduced theory, so now we're working integrally, so maybe I'll write a little z down there to remind us of that. I, j plus 1. Well, now I'm specifying a component. So Li is unfortunately this I here is different from that I there. This is just a component. Maybe alpha's better. It doesn't matter where on that component I choose to make this join, but the component matters. So this is the reduced version with respect to a given component. This goes to the unreduced version of L. And then here again I have the reduced of I, j minus 1 with respect to the component alpha again, and then this goes on, and it just, so this is the co-boundary map, and it raises this by 1. And I should stop, but let me say one more thing about this, that the co-boundary map, so this is a remark, this co-boundary map is 0 modulo 2. And the fact that it's 0 mod 2 is perhaps good because it gives us a little bit of a reality check, because if it's 0 mod 2 and we were actually looking at F2 coefficients here, if the two maps at the end here are 0, it means that this group splits up as the sum of these ones, which is actually more or less what this statement here is telling us. But the other interesting thing about this being 0 mod 2 is that if you look at the integral theory, the unreduced version like this, you'll see that it has a lot of two-torsion. And a lot of that two-torsion actually comes from the fact that it's related to the reduced theory and that this is 0 modulo 2. So perhaps next time I'll begin saying a few words about torsion in the integral theory. Okay, so I'll stop there.